Okay, we are going to get started on Module 6 this week. So that means we're in week 6, which means that we only have a couple weeks left. So time has been flying by. You'll notice that Module 6 is about tolerancing and fasteners, okay? And so between today and the next time we're together, we'll get through that information as far as concepts wise. And those are going to be out of our tech drafting book and all that kind of stuff. And then we have a couple assignments you're going to notice that are going to be in conjunction with this module. And as we kind of get done with things, we'll introduce the things that you'll be ready to work on. Notice that there are no practice problems here. Okay, there's just the 3 assignments. So I don't know if that's good or bad, but that's how it kind of shook out for this particular module. So what I'm going to do is I'm going to head over to our agenda, and we are going to be looking at the tolerancing chapter out of our tech drawing textbook. So I am simply going to open up the PowerPoint presentation that goes along with chapter 12 in our book. So chapter 12 is all about tolerancing, okay? Now we've gotten introduced to this kind of a little bit, all right, through the dimensioning that we've been talking about and doing in AutoCAD. But we're going to get a little bit deeper in here and then looking more specifically at, some fits and things like that. So at the beginning here, they're saying, understanding tolerances. So tolerances are the amount that a specific dimension can vary but still allow it to function properly when it's in its final form, okay? So when we have parts that we're making, we can definitively say that no 2 parts are exactly the same, okay? So what we have to do is we have to understand that, and we have to deal with that, and that's called variation. And these variations can come in from different sources along that manufacturing process. So it can be from the supplier and the materials that we get. It can be from maybe machine capability. It could be from the operator. It could be just the order of operations that we do it in. Something, if we can minimize setups, things like that will all affect how much variation we are going to have to deal with. Now, because we have to deal with that in the manufacturing portion of a product, then when we are creating our drawings, we have to reflect that. We have to take that into consideration. So we can't expect any feature to be to that one dimension. And as we already have experienced with the drawings that we've done and the title blocks that we've created and applied on our drawings, we know that there's a title block tolerance, okay? So we'll be talking about that a little bit later, and that's going to be really the focus of this particular chapter. How can we tolerance? What are the different ways we're going to see tolerances? How are we going to put them on our drawing? And then when do we use different types of fits? Okay, so we'll be looking at that. Now, to effectively provide tolerances on your drawings and CAD models, you must understand in the end how those parts are going to fit together. So if you have 2 parts that are coming together and they're going to fit relative to one another, you need to understand their final function in order to be able to line up and pick the appropriate fit. Is it something that is going to move freely past each other, or is it something that we want to remain stationary? So that might be a clearance fit if it's moving freely, or it might be an interference fit when we want things to, maybe occupy the same space or to be in a stationary mode after they've gone together. You need to have a clear picture of how inspection measurements are going to be performed, okay? Whenever you have a dimension on a drawing, again, with the application of the tolerance, either going to the title block or specifically putting it on our drawing, we have to take into consideration that these parts are going to be inspected later on. So they're going to use our drawing, so it has to be clear what we're expecting so that then they can either accept or reject if the parts don't, meet the specifications on the drawing, okay? Be able to apply tolerance symbols to a drawing or a model. And then also apply functional tolerancing to individual features that are on a part, okay? Now, quality control. Before paying for parts, most companies have a process of quality certification of their parts against the drawing or the model. So for instance, if you happen to be purchasing parts from a vendor, okay, what you're going to have to do is you're going to have to make sure that those parts are actually going to meet the specifications that you're expecting that they're coming in at. So typically there's going to be a little quality process that's going to take place before you actually accept them. Okay. This happens a lot when people are contract manufacturers. So contract machinists or machine houses, for instance, will have parts from a lot of different companies that come in. So they deal with their prints and then they send them to the individual companies. And then once they get back to the individual companies after they've been made, you have to qualify those parts to be sure that they are to the part print. Okay. So as a mechanical designer, mechanical engineer, your responsibility is going to be making those part prints. Okay. Because then the parts are going to be inspected to those. Now, as we look at the tolerances here, you're going to notice as we look at the part, we would show our part in the fashion that we see down here at the bottom. Side view of this pin, front view of this pin, and just focusing only on the one dimension. You'll notice that we have 1.625 plus or minus 2 thousandths, okay? So what that means is we are creating now a tolerance, a band, a target for which the person who is making the outside diameter of this part that they have to hit. Okay. So if you've ever played darts, right? The darts, you have large circles on the outside, they get smaller, smaller, smaller as you go to the inside. And as you can imagine, hitting the bullseye is probably the one that's not going to happen as often as maybe ones that are on the outside. Or if you want to hit the bullseye, you got to practice, practice, practice to get there, right? It takes a long time to refine that skill. Same thing with manufacturing. If we're trying to hit a larger target, it's not going to take that long to get there. It's not going to take many processes to go through to get there. But if my target is small that I'm hitting, my tolerance is small that I'm trying to achieve, now all of a sudden it takes longer time to get there. It might take multiple passes, for instance, on a milling machine. Or I might have to take it off of a current process, put it on another in order to achieve maybe some other tighter tolerances or very smooth surfaces or something like that. Well, each time I have to move that part, each time I have to take more time to get to the smaller target, it costs more money, right? Time is money out in industry. So as a designer, what you want to do is you want to try to optimize that as much as possible. First and foremost, it has to function properly, but you want to give everybody as large of a target as you can, because then, in the end, you're going to be able to save money if you would for the company because it won't cost as much. So as we look at this part, we're saying 1.625 plus or minus 2,000. So we're going to add 2 thousandths to 1.625. So that's going to be 1.627 up here in the drawing. This is the largest size that it can be. Then we're going to subtract 2,000. So 1.623 is the smallest it can be. So when we're manufacturing, we can be anywhere, including both of those numbers, within that zone. And we call that the tolerance zone. Okay. So, and when we have a large tolerance, that's a larger target. So that's going to be like the outside of our bullets, or what I call it, dartboard. And then the smaller tolerances are going to be like the bullseye, the small part of that why is that escaping me today? I am not thinking clearly. A dartboard. That's the word. So I'm looking at different parts and I'm trying to think of two different things at the same time. So tolerance zones. You are specifying those tolerance zones. Very important. And you're thinking about a lot of things, function, but also manufacturing process and capability. Okay. How many are taking cold processes right now? As far as in the program, is anybody taking cold processes, the machining class right now? Depending, okay, I don't have any hands up, so I don't know if anybody virtually is, but when and if you do take that, then you're going to be on different machines in the machine shop, and you're going to be setting up and making parts. And the whole process, the whole purpose of that is not for you to become a machinist, but it is for you to relate to these processes that are going to be used in order to achieve the dimensions that you're putting on a drawing, so that you're thinking in those terms, not only dimension wise, but also capability wise. Now, a couple different things here. We have some size designations. So first of all, a feature on a part is going to be, for instance, a hole, or it's going to be a length, a width, a height. It might be a step, we might call it. So an individual feature is exactly that. Now, a feature of size is going to be one of those features where we have to touch it in two places in order to find what its size is. So a feature of size, for instance, is going to be the outside diameter of our pin that we have here. Another feature of size is going to be the overall length. I have to touch it in two places to achieve that dimension and to, if you would, fully define it. On our block over here, a feature of size is going to be the hole size, okay? And then the overall width, length, and thickness are also going to be features of size. Touch it in two places to determine that. Now, there are also here, there are going to be dimensions that we put on that are going to be related to where something is located. Okay, so for instance, the center of this hole, that could be located from the left or the right edge or from the top or the bottom edge. Those are not features of size. Okay, features of size, like in this case, is going to be a hole, okay, or a length, a width, a height. Okay. Now, as we look at nominal size is always going to be that nice number. Okay, so if we're in the English system, for instance, it's usually going to be tied to kind of standard fractional equivalents. Okay, so if 1 inch, half inch, quarter of an inch, 1 3/4, you know, whatever that might be. That's going to be our nominal size. And that's what we kind of like, that's going to be our, if you would, our base. If we go back to the previous drawing here, 1 5/8 is our nominal value here. And then we put the tolerance on the back of it. So we want, as designers, when we know which units of measure we are working in, whether it's English or metric, okay, we want to make sure that we are using nominal sizes that are consistent with that unit of measure when we are doing things. Now, for instance, if we have a hole and we know we're going to be drilling it, we want to make sure that we don't have an obscure decimal value. We want to tie it to the size of the drills that would be used potentially for making that particular feature, okay? Allowance. An allowance is going to be an intentional type of a fit, whether it is an intentional clearance. That means that we are always going to have the freedom of pushing, for instance, our pin into our hole, and there's not going to be any resistance. Okay, there's actually going to be a little bit of a gap of air, if you would, clearance that's going to be in there. But I can also have an intentional interference allowance where when I'm pushing my pin into my hole, parts of the hole and parts of the pin are going to want to occupy the same space. And in that case, I would have what we call an interference or a force fit. Okay. When I have an allowance that is positive, okay, that's going to be a clearance fit. When I have an allowance that is negative, and we'll be calculating these a little bit later, that's going to be an interference fit. Okay. So not too much right here on that, but those are just some terms. Now, as we look at variations along the length of a feature. So for instance, if we look at a pin, if we look at this pin, you know, that we have here, the feature is the outside diameter here. Okay. And as we look at over its entire length, whatever the tolerant size is, and we don't have that information for this particular part. The nominal size is 1 1/4 in this case. And then some sort of a tolerance, whether it is defaulting to the title block or we would have a tolerance specifically in back of it, that would let us know what the limits of size for that outside diameter would be within, okay? If we look down here, when we have that pin over its entire length, that dimension, that tolerance, that size is going to create a high and a low value for which all of the points along the length of our part have to fit within. Okay, so if this part ends up being, let's say, 2 inches and our diameter is a 1/2 inch, okay? Now, within the tolerance zone that's specified, we could have different shapes occur, okay? Now, these are exaggerated because typically, especially if you're working with plus or minus 2,000s or even plus or minus 5,000s, by the naked eye and you look at something, it still looks pretty darn round, okay? But if you start rolling it on a table, okay, you could probably get the feel for, it's not quite, you know, perfect. Or if it's inspected with micrometers and calipers, or scanned in the quality department, now you can start getting a better picture of what this is going to look like. Now, as long as all of the features, whether it's bowed or you have this hourglass shape or tapered, or you have this barreled shape, as long as all the points still are within the tolerance zone specified on the drawing, they're okay. They're okay. So there's no requirement that they have to be perfect all the way. That's why we have the tolerance. We know it's not going to be easy or even possible to make each one of those parts perfectly straight along their length within that tolerance zone. Okay. So these are things that you can expect when you're producing or when you're specifying the tolerances on a drawing. Okay. Material envelope kind of continued here. So you're going to notice that the material envelope, the actual material envelope, we kind of have this gray layer on the very outside. All right. Then we have our part. Okay. And then the actual minimum envelope on the inside, if you would. Now, physically, it's not going to look like this, but you can see the zone between that outside layer and the very inside layer. That's the points for which all of our feature has to fit within along its entire length. Okay. Now, if it does that, our part is good. Okay. Then it goes on to the next stage in our process. But if the part in any way goes beyond that envelope created by that size dimension, that tolerance, and it's outside of that, we have to reject on that. Okay. Now, sometimes if parts are large, if we, in this case, we've got a pin. If the dimensions are too big, we can maybe put it back on our lathe, for instance, and maybe turn it down a little bit to bring it into the tolerance zone. But if our part is small, we can't bring back material usually because then it's just a little too small. So so that would usually have to be scrapped out and started over. So when we can, we want to try to fix them or rework them, as it's said in industry, and then see if we can bring them in. But by having good tolerances right away on the drawing that are clear and somebody can understand, the job of the designer or the engineer to do that, then the chances of, making good parts are also greater as well. That's part of that. All of our parts are an implied right angle. As you have probably already noticed, we do not dimension 90-degree angles. Okay, we draw them at 90 degrees. It's implied. They still have whatever tolerance is on the drawing border. Okay, it still has a tolerance on it. It defaults to the drawing border, but we don't put them on. It would just get too busy. It would be like unnecessary dimensions. So it's always implied. If you have 90 degrees shown, you don't have to show that angle. Okay. Fits between mating parts. So a fit is a range of the tightness or the looseness resulting from the tolerances that are specified on the drawing, okay, of the parts that are going to fit together. So as we look here on the top, you're going to notice that we have a noticeable gap between the pin that is fitting inside of the hole. So you can kind of see that gap that's created there. So what that means is our pin is smaller than the hole that it's going to go into. So it can easily be put inside. It can move easily relative, to each other. But now if we look at what we have down here, you're going to notice that gap kind of closed up. Okay. Now we're still a little bit small. We're still a little bit smaller. So you'll notice that our pin here is 1.248 and our hole is 1.25, but we can see that there isn't as much, sometimes it's referred to as slop in there, between the two parts. Okay. So now in these two cases, we would have a clearance fit. If we look at the difference between the hole and the hole here, the 1.251 and the shaft, what would that difference be? So 1.251 minus 1.247. What's the gap that's created in this first example? How many? 4 thousandths, right? Yep. If you need a calculator, go ahead. But if you take this number and you subtract this one, it would be a positive 4 thousandths. Our hole is larger than our shaft, right? Okay. Now down here, they did the math over here, and you have 1.25 minus 1.248. Okay. Now in this case, we still would get a positive 2000. So as I referred to earlier, if our value for that fit, or that what we call allowance, is a positive value, then that means that we have a clearance fit. These would go together freely. We wouldn't have to press them. We wouldn't have to convince them, in some way, shape, or form. They're not occupying at all the same space, okay? So this is a clearance fit, and the allowance is positive when we take the hole minus the shaft, okay? So as we look at the example here, so let's take a peek. I just want to zoom in a little bit, come over. I'm actually going to minimize our chat for a moment. So we have two versions of kind of the same setup for the part. We have a pin and we have a hole. And what they've done for us is we're not seeing the drawing, but they're giving us the zones for which the outside diameters of our pins have to be within. So a minimum of 1.247 to a maximum of 1.248. So not a whole lot, 1/1000th of an inch, right? Difference. That would be our tolerance, 1/1000th of an inch tolerance zone, which isn't very large. So it would take us a little bit to get there, okay? Now, as we look at the hole, also 1/1000th of an inch, okay? So again, not an easy one to get, but on a decent milling machine, we can achieve this. All right. So it's not like it's crazy, but it's going to take probably one or two passes to get there. So when we look here, our min and our max of our hole are 1.250 to 1.251. Now, something that you're going to notice here between the two parts that are going to be fit together, you'll notice that our nominal size, 1.25, is on the hole. Why do you think that is? Why don't we see it on the shaft or on the pin? Any ideas? Those who are virtual, feel free to chime in. Oops. Feel free to chime in. Why do you think we're seeing our nominal size, 1.250, which is our nominal size? Why are we seeing that on the hole? It's a typical drill size, exactly. So that's taking the manufacturing process, how we're going to make that feature, in this case, a hole. We want to make sure that we have the nominal size on that hole size, because that's a typical drill. That's something that we would have available to us. It wouldn't be any special tooling that we would have to order, which would cost more money and such, okay? On the pin side, how come the nominal size isn't there? It can vary, but what is the process we would use to make that pin? Any ideas? What type of machine would we use, maybe?
Well, it would probably be a boring, right?
No, it
Or
wouldn't
not
be a
boring.
boring tool on the pin.
Turning, I mean to
It
say.
would be turning, yes. So like a lathe, right? Now a lathe
Yes.
tool is going to be positioned on the outside of that part, right? So now if I need it to be a little bit smaller than the nominal size, a 1/4 inch, all I got to do is push that tool in a little bit, and now I just take a little bit more material off. Okay, but in the case of a hole, we want to go with a nominal size because we're kind of stuck with that. So that internal feature is where we usually want to have our nominal size on. Okay. All right. So, and then you can see the zones here. Now, in this case, we have a clearance fit. If we look at the worst case scenario, the worst case scenario is going to be, well, you tell me. If I look at these two, what is the worst case scenario? What is the tightest fit that I'm going to get? Even if it's clearance, but what is the smallest clearance fit that I'm going to get? Would I use my largest or smallest hole and my largest and smallest pin and compare the two? What would it be? I would take for the tightest fit here, largest or smallest hole? Smallest hole, and I would subtract off the largest or smallest pin. Largest pin. So my worst case scenario is going to be the smallest hole minus the largest pin. So if I do that, if I go over here and I say my smallest hole, 1.25, and I subtract off my largest pin, 1.248, what do I get? 2/1000, positive or negative? Hole minus pin. Positive. So is that a clearance or an interference? Clearance, right. My hole, my smallest hole is still larger than my largest pin or my largest shaft. Okay, good. Now down here, let's look at the values that we see here. You're going to notice in this case, we have the same, oh no, it's not the same size hole. We have 1.250 to 1.2506. Okay. My goodness, 6/10 of a thousandth. That's a difference. That's starting to now probably get into maybe doing a little bit of reaming, I think. Okay. Which again, it takes more time, energy, and tooling. So it's going to be more costly, but that's okay. But then over here, you're going to notice that we have 1.2513 and 1.2519. Right away, when we look at the size of the pin compared to the size of the hole, what type of fit do we have? A clearance or an interference? Interference. And this is what I was referring to you before. We literally have these two parts wanting to occupy the same space. Okay, we want them to occupy the same space, or by their dimensions, they are going to now not be easy to get together. They're not going to freely flow together. We're either going to have to press them with something, or we might even, in some cases, put one of the parts in the freezer and we're going to heat up the other one and put them together because we want to use, our physics, if you would, to try to convince them to get together and let them cool to room temperature, and then they're going to stay together. Now, I don't want to give the impression that an interference fit is bad. It's not. It's an intentional type of a fit. Okay. So it just happens to be at times we want things to fit as an interference relative to one another so that they don't move. Oh, I should have my arbor press in here. It's in the other room that I lecture in. But our second year students they modeled an arbor press, and the arbor press physically is in the other room. And one of the pins that goes into what we call a table plate stays in there, but it is not screwed in. It's not glued in. It's not welded in. It's pressed in. Okay, so then it stays in that very same space when they are, together as a function. So it's an intentional fit. Okay, so in this case, if we look at our worst case scenario here, our smallest hole and our largest pin, what is the allowance that we're going to get? So we're going to have our smallest hole, which is going to be 1.250, minus our largest pin, 1.2519. So if we subtract those, what is our number? Hole minus pin. First of all, positive or negative value? It's negative this time, right? Because this number is larger. So 1.2519. And subtract that off of 1.250. So it's going to be what? 0.0019 interference, right? It's that different. So it's these two numbers right here. Now that doesn't seem like a ton. Probably could tap these together. Maybe not. I don't know. Does anybody have experience with press fits? This is like almost 2 thousandths. Is that a lot in metal? We might have to put it on an arbor press, right? Right, probably put it on an arbor press, but not crazy, right? It's not crazy. So if you start to get into a couple thousandth, that's when you usually have to do a little bit of heat and cooling to get them together. Okay. And then especially if you're dealing with things like bearings, those are going to be press fits, but they have to be out to the 4 and 5 decimal places, because you want to make sure that the race is going to be stationary inside of whatever housing you're putting in, but you don't want to collapse it too much with too much interference. Otherwise, the rollers in that bearing aren't going to properly roll. So there's different types of fits for different types of elements that you have to take into consideration. So if it's something that's going to be metal on metal and you just want them to stay together, then usually, a couple thousandth is maybe reasonable. But when you're starting to look at precision types of machine elements like bearings, now you have to start. I'll tell you a story about bearings. So I was that was something that we used a lot in high-speed packaging equipment when I was at Hyson, and that was my first job as an engineer. And we were holding, for bearings, like a ball bearing, we were holding, 4, 5, 6 decimal places sometimes. And they were quite critical. And so they were considered a precision element that we'd have to deal with. And I got a new job and I went to Slinger. It was Dyco, but I think it's Carlisle now in Slinger. And when I went on my tour, when I was interviewing, I saw them press fitting bearings into a just a non-machine welded hub on a wheel for, let's say, a garden tractor. Now, when I was at Hyson, we had very high speed packaging equipment. So I mean, when I say high speed, this was like the winders for toilet paper, paper toweling. You can imagine how incredibly fast that those go. They do, and you need them to last, a long time. So we were super precise on those because we wanted those to be properly lifed and all that kind of stuff. Well, the application of a lawn tractor, just going at a very low speed on not on the highway isn't as critical. So they were just pressing, and I'm like, oh my gosh, you're pressing in berries. And they're like, it's the application. So it's really the final function of what you're going to be looking at and how that's going to affect things. So we didn't need a huge life out of the lawnmower tractor or the lawnmower hub bearings as opposed to our high-speed wrapping equipment. So know your application, and you're going to see differences, in those tolerances and what's appropriate. All right. Specifying and using limits. So the limits of our tolerance zone are going to come directly from the tolerances that are applied on the drawing. So every one of the dimensions that you put on a drawing, and you guys have been putting dimensions on, has a tolerance, and it's going to come from one of two places. It's either going to default to the title block, as we've talked about, or it's going to be specifically specified in back of the tolerance that is, on the actual drawing. And you guys have had experience with both. And the drawings that you guys have been working on for me, you've seen limit dimensions where you're showing that high and that low value. And you've also been just having the single number that defaults to our title block. Okay. So as we look here, you're going to notice that, let's see, the loosest and the biggest fit. Okay. So as we look here and we look at the limits of the dimensions. So here you're going to notice that over on the left-hand side. Now, this isn't an official drawing, if you would, but they're showing us the limits. The limits is that difference between the high and the low value. Limit dimensions, I believe, are the best to put on when you want to absolutely make sure that somebody doesn't do a wrong mental math error in their head when they're making these parts. So for instance, you have a difference of only 1/1000th of an inch on the size of this pin. If you put, and maybe 1/1000th isn't a great example, if you put 1.248 minus 1/1000th of an inch plus 0, there hopefully aren't many people that are going to make that math error. But if you have plus or minus 6/1000ths on there, you can imagine that, oh, I got to add, I got to subtract, and that could be a problem. And when you're the designer, you want to eliminate as many of those types of things. So when I was at Hyson, my high-speed packaging equipment place, where we had very kind of precise things that we were dealing with, we always had to put limits on all of our dimensions if they did not default to the title block. That way, whoever was making them, whether it was in-house or outside, they had the highest and the lowest value, and there was no question on what was acceptable. Okay. So I would always, as the designer, especially when things are critical, I would always default to limit dimensions if they're not going to be defaulting to the title block. Okay. So here are our limit dimensions, those difference between the high and the low, only 1/1000th of an inch, and then here 1/1000th of an inch as well. So as we look over here and we look at what parts were actually made to, you're going to notice here that we have this one made to the smallest size pin and the largest size hole. So to find that difference between the two, you're going to notice that what they did was they found the allowance by taking, I'm sorry, it's the bottom one here. I don't know why they did one and then the other. They took the 1.251, which is the hole, minus the pin, which is 1.247. So it's always hole minus pin. We get a positive 0.004. That's the maximum clearance that we're going to see. Kind of like to say it's like the maximum amount of slop, if you would, that you're going to get. You're going to get those. You can actually be able to feel the pin moving around inside of that hole. The minimum clearance, okay, in this case, is going to be the smallest hole minus that largest shaft. This becomes our worst case scenario in this case, okay? So here you're going to notice that we still have some clearance, 1.250 minus 1.0 or 1.248, so a 0.002 difference between the two. Both are positive, so they're both a clearance situation. Okay. We're just going to skip over this one. Whole system. We've already kind of alluded to this already, but tolerance dimensions are commonly determined using what we call the whole system. The whole system, what it says is that we put the nominal size on the whole for exactly what we had identified earlier, because we have standard tooling, drills, and such that are going to be to standard sizes. Okay, so they're easy to achieve when we want to remove that material. And then we do an allowance on whatever the pin or the shaft that's going to fit into that hole. Okay, so here you're going to notice that on this case where we have our tolerance applied, we have a diameter of a 1/2 inch, and then we have 0.502 as its largest value, but you see the 1/2 inch at the bottom of the hole size here. Now, something that I don't know is intuitive if you haven't taken the manufacturing processes class, but many times a lot of students will assume that if I have a 1/2 inch diameter hole and I'm going to use a drill to create it, as a drill dulls, did you guys know that the hole actually gets larger? Do you know that? It's not intuitive because you think as it gets dull, the material must have come away from the edges of that drill, so it's going to make a smaller hole. Why do you think, and it doesn't happen, but why do you think a hole gets larger as a drill dulls?
Better?
Okay, wait, I got 3 answers. Roman, what did you say? It's not cutting clean. So what's happening to the chips? That's okay. Deborah, what you were going to
They're
say?
built, they're building up.
Metal starts flaring out.
The metal starts filling out. Carlos, what were you going to add?
Like the chips, won't they like build up and cause more friction, I guess?
They do. They actually do. So what happens is, and it really the combination of what the three of you had just said, those chips that are on the inside, they get to be bigger and chunkier, and they actually start working that hole as they try to come out. Okay. So whenever we specify a hole size, your nominal size will be the minimum size, and then you're going to add tolerance to it. And again, this is a function of the manufacturing process on how that tool actually reacts over time. You want to give it time. I mean, we're not expecting the tool to stay sharp forever, right? We're expecting it to dull. So that's why your tolerance will only be on the high side, not on the low side. You start with your nominal at the bottom. And again, this is due to a standard size drill. Okay. And that's called the hole system, where the nominal size is on the hole side. Okay. The shaft system is just opposite. We've got a nominal size on the shaft. This happens when we have specialized type of shafting that might be ground and hardened to a certain size. And a lot of times that nominal is going to be in there. So that means I'm purchasing, specific special material. And then I'm going to have to put the allowance on the hole size. And in this case, you might have a couple of things that you could do. You could either bore it out like on a CNC machine, and then it would just interpolate and make that hole size. Or you might have to have special, tool made in order to create that. Okay, which isn't the end of the world if this is what's required. I don't want you to go away from things, but I also want you to understand that you don't want to be specifying a hole diameter like this unless there's a reason for it on the shaft side. Okay, this is what you are going to tend to do for, the nominal size on the hole for about 90+% of what you're going to be working with. These are exceptions and special cases. Okay. General tolerancing notes. So all title blocks are going to have this, all tolerances are, unless otherwise specified. So as we said earlier, any dimension that we put on a drawing, we know we are going to have a tolerance on it. It's either going to default to the title block if there isn't a specific value in back of it on the drawing, or the value is going to be specifically there. So, so you're going to notice here that they have a general note. All tolerances are, and every company is going to have their own standard. Okay. You can never change the title block tolerance. WCTCs that we have are for one place decimals, it's plus or minus 0.03. For two place decimals, it's plus or minus 20 thousandths. For 3 place decimals, it's plus or minus 5 thousandths, okay? So if you have a 3 place decimal, there's still a tolerance on there. It just defaults to the title block, okay? And if you wanted to figure out what the limits were, you're gonna add and subtract, you know, whether it's 20 thousandths or 30,000 or 20 thousandths or 5 thousandths. When it's metric, I forget what ours are because we don't use metric all that often. We use English more often, but we would look to our title block for that as well. Okay. Oh, I happen to have them here. So if I go underneath my camera, what I'm referring to, just in case, there's a note in our title block. Okay. Right here is where we have our standard tolerances. All right. So you'll notice here, oh, I didn't say that right. So for a 1 place decimal, it's plus or minus 0.1. Sorry, a 1/10 of an inch. I was thinking it was a 30 second or a 32nd of an inch. 2 places plus or minus 20 thousandths, and 3 place decimal is plus or minus 5 thousandths. Okay, so for any dimension that I have up here, it looks like most of these are all 2 place decimals. They're all plus or minus 20 thousandths. Okay, so there is a tolerance on each and every one of these dimensions. Because I don't have anything in back of it, it defaults to the title block. Okay, that's on all drawings, all drawings. If I have a metric, if I can find a metric, oh, here's a metric. On this one, you're gonna notice that 0 place is plus or minus 1 millimeter, and a 1 place decimal is plus or minus, I think it says 0.1 there, okay? My eyes, I don't have my reading glasses on right now, okay? We never change this title block. So if you're like, I'm doing 2 place decimals and I don't want to use plus or minus 20 thousandths on these, and I don't want to put a tolerance in back of all of them, I'm just going to change the title block to plus or minus 30 thousandths because I think that's better. Not acceptable. You never change the title block on anybody's drawing. Okay. And I hope that goes without saying, but I think it's worth saying because it's really important. Because other people become accustomed to that. And even if you say, oh, well, it's down in the title block, nobody's going to look there after they know what the tolerances are. Okay. So, so you can use those. So always know, and you want to intentionally put that tolerance on there. So if you have a 3 place decimal, you're in your mind as a designer, plus or minus 5 is good. 2 place decimal, plus or minus 20 thousandths, that's good. You're thinking about that tolerance on each and every one of those dimensions. We already talked about limit tolerances. So limits are going to be, and you've seen these on some drawings already that you've done. And that is when we're showing the actual zone, the target, the high value and the low value. Okay, so this is called a limit dimension. Again, it's the best one to use, especially when you have critical dimensions. When they get out to 3 and 4 decimal places and you're only holding, you know, a couple thousandths, limit dimensions are really a good idea, okay? Because then nobody's going to make any mental math errors in the process. We're going to skip over single limit dimensioning. Well, I'm not going to skip over it, but all they do is you're going to notice that they give you, they note a min or a max on the actual dimension. So it's kind of funny because what I don't like about this illustration is I've seen this before when you have a min and a max and it's a limit dimension with a min or a max in back of it. And there's not one min or a max on any of these dimensions on this illustration. So this is the one that the book is referencing. But anyway, so we're just going to kind of skip over that. It's not very typically done where you see a min or a max because especially if you put it in a limit form, you know which one is min, you know which one is max. So the next types are where we have plus or minus tolerances. And there's either unilateral or bilateral. Unilateral means that the tolerance applies just in one direction. So you'll notice that over here, 1.878 plus 0 minus 2. Okay, so that means that we're only giving it minus 2 on that dimension. So all of the tolerance is in one direction, unidirectional tolerance. Bilateral is where I give some on one side and some on the other. In this case, you'll notice you're plus 2 minus 1. In both of these cases, they're relatively critical, okay? I would do limit dimensions. Again, think about the end result. If it's something that's even close to being critical or something that's an important dimension, you don't want a mistake to be made. Limit dimensions give you a clear high and a low, okay? Angular tolerances. Here again, the most common value, I believe, is plus or minus a half a degree. Okay. If it needs to be something other than that, then you want to specify it. Okay. And that's what you see here. But most often, unless it's a timing issue, like on a camshaft or something, the plus or minus a half a degree is usually pretty okay. Tolerance stacking. Okay, tolerance stacking. Now, when you guys take GD&T, geometric dimensioning and tolerancing, it's this class that we spend kind of looking much deeper into tolerances. This class gives you an introduction to them, starts you thinking about them. But as we progress through different courses in the program, you're going to get a little bit more, a little bit more, a little bit more. And tolerance stacking comes up in GD&T, and this is a great illustration for it. So you're going to notice that we have two different ways of dimensioning and tolerancing the same part. Okay. So here you're going to notice we have 3 steps. What this is called, the type of dimensioning that we're seeing here is called baseline, where all of the dimensions are coming from one side, or sometimes referred to as a datum. Okay. And basically what we have to our first step, we're saying, all right, 1 to 0.95 or 0.995, 2 to 1.995, and then 3 to 2.995. So at any given step, I'm only getting a difference of 5 thousandths, right, on each one of those steps. And individually, that's as far as they can go, 5 thousandths, 5 thousandths, 5 thousandths. Now, if we take the very same part, we dimension it a little bit differently, called chain dimensioning it. So I start with the 1, at on that left-hand side to my first step, and notice that I have plus or minus 5,000, or I'm sorry, not plus or minus, just a difference of 5 thousandths. Then if I go to the next one, it's dependent on where that one ended to where it's going to end. So if this first step, X, let's say was at 0.995, now this whole step is shifted, the next step is shifted 5 thousandths to the left. Do you see that? Or if it's made at the 1 inch, it's shifted 5 thousandths to the right. Okay. So it is dependent or relative to the previous step in this case. All right. And then the third one, by the time we get here, it is dependent not only on that first step, it's also dependent on the second step. And now it then has a tolerance on it. So the total tolerance as we get to the end here, in this case, it's going to be 5, 10, 15 thousandths, that this can be different at the end. Okay. Where here, if I go just from the baseline and I go right to the end, only 5. So your function is going to dictate how you dimension this. Now, am I saying one is better than the other? No. But if you have the intent that it's critical that this side is to 5 thousandths, then this is the way we dimension. But if it's not so critical, then this is fine. And how it's set up in the manufacturing process is dictated by how you dimension. Okay. How you dimension. So, so keep that in mind. This is what we refer to as tolerance stacking. If you work in industry, you might have heard this before. And just the way that dimensions, they accumulate depending on how we actually put our dimensions on. So when you're considering the end result of your product, how you dimension baseline or chain dimensioning is going to make a difference. Okay. All right. So there's a lot to think about. It's an important job. I mean, you think, oh, it's just a drawing. No,
Yeah.
drawing. It's not just a drawing. And why do I say that before we go on? I'm not dictating like one is better than the other, but why is a drawing? Why do I tell you guys creating a drawing is really important? Oh, I'm sorry. What was that? I don't know if somebody virtual is trying to talk.
Okay.
Oh, Ethan, I
Wow.
think I'm having a hard time hearing you.
Hello?
Yes, now I can hear you better.
Sorry. My dad came up.
Were you responding to my question or no?
Oh, no.
Oh, okay. All right, no problem. All right. So why do you think a drawing is really important? Kind of thinking about the things that we've been talking about tonight, thinking about manufacturing process, thinking about the tolerance levels. Why is a drawing important?
To make sure that it gets made correctly.
Yep, made correctly, and not only made correctly, Carlos, but economically. Okay. And when I say economically, that's the cost of the part, right? Cost of the part. Now, we talked a little bit earlier about tolerance zones and how small tolerance zones are probably going to take a little bit longer or maybe a lot longer, depending, compared to large tolerance zones to create, right? And I think I had kind of said in passing, time is money, right? So the longer it takes me to make something, the more expensive that part is going to be. And if we unnecessarily put tolerances on that are super close, might fit great in the end, right? And it'll go together perfectly all the time. But if we can't make that part economically and there's not a profit left where we can sell our part, and there's that difference in process and that difference in, how much it's manufactured, how much we can sell it for, what happens? What happens?
You go bankrupt or you lose
The
money.
company's going to lose money, right? And the reality is, I don't work for free either. Okay. So I'm not saying anything. We all trade time for money, right? And when we go to work for a company, our hope is that next week we're going to get our next paycheck, right? And if we can't be profitable, that's not going to happen. And I'm telling you that when cost reductions need to be created, especially in the manufacturing process, the first thing they're going to do is pull out the drawings. They're going to look at every one of the tolerances and they're going to say, is this one necessary? Is this one necessary? Is this one necessary? And you want to open up as much as possible. You as the designer need to take that into consideration up front. You want to make sure that you're maximizing the tolerances. You're not putting stuff on that isn't necessary. And sometimes that's easier said than done, because when we have CAD tools, for instance, where we can just set the tolerance zone to 2 places, and that looks really good on the drawing, but is that functionally what we want? Okay. Not only, whatever's fitting in here, but will it fit in the space that we need it to be in? Do we need some of these? So each one of these dimensions, you need to think, what is the tolerance I need to be on there? What is the function? I realize we're in the early stages of this, but you need to just kind of have that in mind. It's not just in a vacuum and just doing what the drawing guide says. You also are then going to be, when you're out in the industry, thinking about, how are we going to make this? And then the other thing is, and this isn't, I know I'm kind of getting not really off track. This all is related, but what can you do in-house as opposed to having to send it out? It's always cheaper to keep things in your building and make them there if you have those capabilities. So as a designer, you want to think, can I run this across our milling machine that, we have right here? Or do I need 5 decimal places? I have to send it out to be ground or reamed or whatever it might be. Okay. And if you do, that doesn't mean you shouldn't. You do. You just need to do it because that's required for the function, but you don't want to do that for every dimension, right? You don't want to do that for every dimension. You want to make sure that you're utilizing the capacity that you have, because it's always cheaper to keep things inside than send them out. Okay. Because then there's transportation costs and shipping and all that kind of stuff. Okay. So there's so much to think about. It's such an important job, and I'm so excited for all of you. I love doing this job. It was really good. I love teaching, but I loved doing the job too. It was really great. All right. American standard limits and fit charts. We are not going to be looking here in this class. This is one of the subjects that you're going to be getting when we do GD&T, and also when we do our engineering design projects course. Okay, we're going to be doing more of this, but what is really nice is that there are standard charts out there. When you decide what is the type of fit that I need, whether it's a clearance fit or an interference fit, you're going to be like, okay, here's my nominal size. And there's charts that are going to give you the numbers right away. Okay. So you don't have to reinvent the wheel or try to figure out, how much I need for interference or not. So there are charts that help us with that. The other thing that I think is really important, and this is, again, kind of speaking off of that manufacturing processes side of things, is there are certain processes that can hold certain tolerances, that are capable of tolerances. So as we look, and I'm going to actually start in the bottom right-hand corner here. In the bottom right-hand corner, you're going to notice that the processes that they're referring to are listed on the left-hand side here, okay? And down at the bottom is drilling. And if we go all the way over to the right and we look at the sizes that we have here, you're going to notice that these numbers on the right-hand side of our chart are larger, thousandths of an inch, 10 thousandths, 20 thousandths, are larger than the sizes that we see at the left side of the chart, okay? If we look at the top manufacturing processes here, these have to do with lapping, honing, grinding, broaching, reaming. These are going to hold very small tolerances, okay? So if we're specifying things to 4 and 5 decimal places, we're hanging out on the left-hand side here. These are small targets to hit. Not that they're impossible, but they require secondary and even maybe tertiary types of processes in order to achieve them. So when you lap something, you don't just lap it. You've got to first drill it out, bore it out. Then you're going to be probably grinding and then getting the honing and lapping. That's 4 processes. That's a lot of money to get there. Okay. Again, not that it's not necessary in some cases, but you want to make sure that that's what you absolutely need. Okay. Over on the right-hand side, mills and drills and turning equipment like lathes, these are all going to be found in a pretty run-of-the-mill, relatively up-to-date shop, right? That can make parts. So down here on the right-hand side, this is where you want to try to live with your designs. Even if you're not going to do it in-house, there's somebody down the road in Milwaukee that's going to be able to do it for you relatively cheaply and quickly. Okay. So up here, again, special circumstances. All right. And they're going to be very high cost. So that's really what the point is here. The other rows that you see are the size ranges. So what you're going to notice is that when you're in small size ranges, so think holes and pins. If I'm anything below or right around an inch, that's going to be the top 2. And so those are going to be kind of parts that you're going to hold in your hand, if you would. As parts get larger, they're just naturally harder to hold the tolerances. So even if you're on the same process, because the part is larger, those capabilities are actually not going to be able to be held. And that's consistent with all of the processes. So it is size dependent. Metric system and tolerances and fits. So the metric system also has the ability to, create their own allowances and fits. And they have different standards, if you would, to the tolerances that they use. But it's still the same type of, fits that we have. So instead of calling them RC, which are running clearance fits, they're going to have a different designation for them. And that's really just the difference. But it's still looking at and comparing the minimum size hole to the maximum size shaft to determine the fit that you have. Okay, so it's just that the numbers, decimals are going to be different, and that's okay. The next slide that we have here is talking about geometric dimensioning and tolerancing. We will not be doing any geometric dimensioning and tolerancing, known as GD&T. If you work on an industry, you've maybe seen these symbols on drawings, okay? And what they do is they speak to form and function, and their refinements on what our rectangular coordinate dimensioning, which is really what we're talking about here, can do. Now, it's kind of funny because we have a whole separate class that you get to take in this program, and I think it's 80 hours total, okay, over 8 weeks, just on GD&T, okay? But the standard actually marries both together. We use rectangular coordinate dimensioning in conjunction with GD&T. But when we teach it, rectangular coordinate dimensioning is just kind of more intuitive and easier. So when we're learning AutoCAD and we're learning how to set up drawings and we're learning the rules, we're not going to introduce another thing here. So this is going to come. So, but you notice that there's a set of symbols and there's going to be considerations that we have when we design them into our parts. And we'll talk specifically about that in GD&T. So that is coming. So if you're wondering, do we learn that here? No, not in this class yet, because we got to kind of get more experience under our belts and then we'll add this on, but it is part of the total standard. Applicable symbols to position and form. So these are the standard symbols that we see. When we see GD&T on drawings, we're going to notice that we specify it using feature control frames, datums, to kind of specify what we need here. So when we have boxes around things in that GD&T class, you would learn how not only to apply this, but how to interpret this. Okay. And yeah, so that'll be left for another class. You get to look forward to that. How about that? So that takes us to the end of our lecture on tolerances. So what I'm going to do is I'm going to stop our recording here.